Welcome to a new video about control realization. We do that in this example number 5 about the lag controller, also called the phase lag. We will see step by step how we get to the circuit we want for a specific transfer function. So the calculation will be given step by step, and also we will verify our calculations with SPICE simulations. So we have the following design problem. We would like to design a physical electric circuit for a given lag controller transfer function, which is shown here. We see there is a 0 at minus 0.2 and there is a pole at minus 0.01. The pole is closer to the vertical line in the complex plane than the 0. That's why we have a lag or the phase lag controller here. So let's look at the solutions. There are many options, of course, to make this circuit or make a circuit that will generate or mimic this transfer function. This is one of the options. This is just a very simple option. We have three unknowns, R1, R2, and the capacitor. So we need to calculate these three values. So let's start with a very generic expression for this transfer function of the circuit, because we like to know what the ratio is from the output divided by the input. That is really what is mandatory. And for that we can use nicely the voltage divider rule we know from electric circuits theory, and that will give us the new transfer function H, which is then VO over VI, and these two are in the Laplace domain. That's why we have it in capital letters. So we can say the VO over VI is actually this impedance seen by the output node divided by the impedance seen by the input node. That's actually shown here. So that is the impedance, the numerator, seen by the output node divided by the impedance seen by the input node. Now the capacitor has a reactance that is 1 over SC. And then you have R1 plus R2 plus the reactance, and the other one is R2 plus the reactance. That's actually shown here. Now we need to further simplify this, because we have a fraction in the numerator and another also in the denominator. So we have a fraction and a fraction, so that's not really readable. Let's then multiply the numerator and the denominator by the SC. Then you get the following expression. So you multiply this by the SC and also this one. You also multiply the complete thing here by the SC and also this one. So this will be 1 and also this one. So these are the ones. This is R2 times CS, and this is an R1 plus R2 in parentheses times CS. So that's the expression what we get here. Now we need to do now the couple of steps extra to get this transfer function closely in the format as given by the G-lag. What can we do? Now we need to isolate actually S. So we need to have a coefficient in front of S which is 1, because that's also what we have here. So we can do the following. Let me describe what's happening here. Now the R2 and the C is now taking out of the parentheses, and then you have now the S isolated. But then this 1 must be done 1 over R2 times C in order to get, again, by if you multiply out this one, back to the original situation here in the numerator. The similar is done in the denominator. You can see that coefficient or part in front of the S, R1 plus R2 times C, is taking out, and then you do 1 over that exact same term. Now we can see that this is more closely or matched with a G-lag transfer function. Now we can simplify this further because the C will cancel out, so we can divide it out. And we also have that R2 over R1 plus R2 can also be taken out as a coefficient, as a multiplication factor. So this is given here. So I use colors here to identify that easily. So this is the part for the, let's say, the coefficient, R2 over R1 plus R2. There's also a red part, which is then this, and there's also a blue part here, which is then this part. So we have now the following. This is the 0. So the 0 is given by the minus of this value, 1 over the R2 times C. And there's also a pole, which is then given by this, which is then the minus of the 1 over the R1 plus R2 times C. And this coefficient is then also the sort of the attenuation factor or the gain factor for this transfer function. So we need to move on in order to find these values for the resistor and the capacitor. So let's compare then the transfer function of the G-lag and the transfer function of the circuit H. Okay. The first thing we can say is, if I look at this transfer function, and this is that the red one is the 0.2. That's what we have, the first equation. And the blue one here is the 0.01. That's the next one. Okay. We have now two equations, but we can say we have also the third one. Is that really the case? Let's check that, because 1 over 20 must be, or should be, that is actually what we can say, R2 over R1 plus R2. But do we have then a new equation? Because these two equations are independent, so they are not related. Because if I make a new equation, let's say 0.2 times 2, for example, 0.4 is equal to 2 times this one. That is not a new equation, it's the exact same equation, but just a different format. Is this really a new equation? Let's see that, because R2 over R1 plus R2 is then 1 over 20. But if I look at this expression, I can say, for example, 0.2 or 0.01 over 0.2, that's also 1 over 20. So the thing is, that means then I have the ratio actually here between this pole and the 0 can also create this ratio, which is also 1 over 20. So it is not a really new equation. That's the reason what we actually have still two equations only, and we have three unknowns we need to determine. So we really need to select a parameter, and in this case I select the capacitor again, because that is most of the time not easily found compared to the resistors. In a practical case we take that, and in this case I have chosen for a capacitor of 100 microfarads. Then I can use this equation in red to calculate the R2. So we can now calculate the R2 using this formula, and we have then 1 over 0.2c, because that is the expression you can get in order to calculate the R2. And if I now substitute everything here, because 10 to the power minus 4 farads for the capacitor, and if you now do the calculations here, you get 50 kilo ohms. Okay, that's for the first step. What can we do next? Now we can look at this equation and then substitute there the R2 we have calculated, and also the C we have selected, so we can then get the R1. But first we can rewrite this as 1 over 0.01 is equal to the denominator that's shown here. That's the next step. And then moving on to divide out also the C, so the left and the right hand side will be then divided by the C. So you have this expression, and then you can now express R1 in terms of the other parameter. This is now the mathematical expression for the R1 in terms of the R2 and the C. Do we have the C? Yes, we have the C. So that is equal to 10 to the power minus 4. We do have the R2, yes, also it's 50 kilo ohms, so we can just move on and substitute the here values. So this is the 50 kilo ohms, 10 to the power minus 4 is for 100 microfarad, and if you now do the calculations, you will get 950 kilo ohm. So that is the next one. Is also the final actually, because R1 and R2 and the C is now determined. Okay, let's now continue with our analysis and then looking at the simulation results and specific the frequency analysis. This is the Bode plot for the gain, the blue one, and this is the gain, this is the frequency, and this is the phase, looking at the phase for a specific frequency. You can see the phase starts at 0 and then drops and then reaches a minimum value and then increases again and then reaches again 0 for higher frequencies. So it starts at 0 degrees, sort of gets a minimum of minus almost 65 degrees and then moves up again for higher frequency to 0 degrees. But let's start with the first thing, that is the low frequency gain, which is 0 dB. Is that true? Now let's see what we have from our transfer function. Because the low frequency gain, if I look at the lag, if I substitute for S 0, then this is 0, that is 0, that means 0.2 over 0.01, that is 20. So that means we have here then 1 over 20 times 20, that is 1. So in scalar form we have 1, but in the magnitude, in the Bode plot, we of course use dBs, so we need to have 20 log of that value will give you need 0 dBs. So that is verified. The next one is the other extreme, which is the high frequency gain. That is here calculated as or determined by the simulator as minus 26.02 dBs. Let's check if this is really the case, because if I look at the high frequency gain, that means actually S is approaching infinity. It means G lag for infinity. That is mathematically, of course, not correct, but we do it anyway. We know what we are doing. So it means the S is very large, let's say 10 million or 100 million. it doesn't matter. And then we have then very small addition here, so in the limit, this is just 1, this ratio. That will mean 1/20 is actually the gain, or the scalar value for this G lag transfer function, and then this is the value in the scalar form. But again, if we want to calculate that in the dBs, we do again 20 log of that value, and it will give you minus 26.02 dBs. Again, verify that this is correct. So 1/20 is also 0.05. Okay. We see also two other labels here that are important because we have a 0 and a pole. So let's also check that. This is the pole frequency because this line will now drop. That is due to the pole. So the pole comes first. That is at the frequency of 1.595 millihertz. So 1.595 millihertz. But we need to, of course, move to the radians per second. That is then multiplying this by 2 pi. Then you get 0.01 radians per second very closely. Then that is indeed the pole. So we have verified this. The next one is the 0 frequency. Now from the Bode plot we see it is 31.76 millihertz. Again, we multiply by 2 pi and you get 0.2 radians per second, which is then our 0 frequency. One note about how to determine the pole and the 0 frequency. Now you see this is the low frequency gain. That is the reason for calculating this low frequency gain. It's 0 dB. You go down by 3.01 dBs and you determine this frequency. So you go down here and you determine also the reduction in the gain here by 3.01. The same thing is here because this is the minus 26.01 dB. You go up by 3.01 dB, so you then determine your 0 frequency. Similar thing here, but then the reverse, you go up. We had here nothing actually in the low frequency part. Then the pole is dominating, and then the 0 is approaching, and then it cancels actually the effect of the pole. And then again, everything is the same as before, of course, then lowered in the gain. We also see the phase contribution is almost minus 65 degrees at max, as said before. Alright guys, this is our example about the lag controller, physical realization using electric circuit, and we have seen that this circuit will do the job using the 50 kilo ohms for the R2, 950 kilo ohms for the R1, and also the C we have chosen as 100 microfarads. If you have any questions, comments about this example, please let me know in the comment sections. I will try to answer them as soon as possible. See you next time in another video. Take care.